our plan for next 10 years is to have this in the real world, right? Not being in the science fiction. We want them to be part of the real life.
This is the Discovery Files podcast from the U.S. National Science Foundation. I'm Nate Potker. Whether fully autonomous or in close collaboration with humans, robots are becoming more prevalent throughout people's lives. From the factory floor to the operating room to space exploration, the field of robotics is deeply interdisciplinary, combining advances in engineering with innovations in computer science. As technologies advance, so do the possibilities for what we might use them for. We're joined today by David Saldana, Assistant Professor in the Department of Computer Science and Engineering at Lehigh University. His research focuses on developing resilient and adaptive multi-robot systems capable of operating in unpredictable environments. Dr. Saldana, thank you so much for joining me today.
Oh, thank you very much for the invitation. It's a pleasure for me to come and talk a little bit of what we do in our lab.
As we move into the research work, you're dealing with multi-rotor aerial vehicles. Is there a difference between those and what people generally just call colloquially drones? Like we're talking about small drones, right?
Yeah, it's basically the same concept. When the multi-rotor systems, they could have four. It could be a quadrotor, it could be 8, it could be 6. But it's the same idea. It's just a vehicle that it's in the air. It could be small, as you mentioned, but it could also be big.
So what are some of the ways these kind of vehicles are currently useful?
There has been a boom in their use since the last 5 to 10 years. We see them as toys in Christmas. We see a lot of photography in real estate. You can see that now people like the high view of their houses. In military purposes, drone delivery as well. So it has been becoming more popular. And what what we are trying to do is like to move something that 20 years ago seemed like unrealistic or just like a sci movie. We try to make it real.
How do aerial robots grab or manipulate things?
Traditionally, what researchers did in the last 10 years was when they needed to move an object, they put a mechanism on the drone to allow it to grab and move the object, right? So we talk about grippers. We added some grippers to them, robot arms, but these mechanisms are very heavy and they are difficult to operate. Right, like the drone doesn't have to move its body anymore. It has to also move an external body that is articulated and brings more problems to the system.
I know you're developing hitches as a different approach. Can you talk a little bit about how hitches might be beneficial in, say, the construction industry?
The arms are heavy and they need power. They are expensive. Now we are proposing something that is completely different. We are proposing something that is light. It doesn't need a battery. It's very low cost, very cheap. Now the challenge is how can we do that, right? Humans have been using ropes for centuries, since the beginning of the humanity. But they are not that popular in robotics. So we want to bring that archaic technology and provide this new capability to the aerial robots, right? So now that we have ropes, we have a drone that we call the catenary robot. It's basically 2 drones connected with a cable. The curve that the cable describes is called the catenary curve. And based on this catenary robot, we can have many of them and they can start to interlace the cables. They can start to move around them and move around the object. So we can tie the objects and we can move the objects. Specifically in construction. In construction, we need to move materials and tools from one place to another. That's what the builders do all day, moving objects around. So we want to give them a new tool and a helper who will come and move the the objects to difficult places, like in the skyscrapers when we have like very high locations. The drones will be able to pick the tools from the ground and take it to them.
When you're using drones to try to move things, what are some of the challenges you run into?
The main challenge comes from the ropes or the cables that we try to manipulate, because they can have infinite configurations, different infinite shapes. So we need to give the capability of the robots to manipulate those cables, right? To slide them from each other. One of the difficult problems that we face is trying to tie the knots. Once we make the knot, tying it's a complicated task for the drones, especially because that depends on the material, how the rope was fabricated, how elastic it is. So we had all these properties, and the way that we do it is by interacting with the cable, right? We humans, we are really good at that because we have experimented with many ropes and we understand how they work. But for robots, they need to come and see like, okay, if I pull, this is what's going to happen. And it has to be coordinated because we are trying to do this task with cooperative robots. So if I pull, I shouldn't pull too hard that I will pull my colleague there.
One of the things I had been thinking about before this conversation is how are they interacting when they're in a swarm configuration or collaborative state? Like how much are they aware of each other?
Especially in this concept of making hitches and making knots in the air, the fundamental robot that we have is two drones carrying a cable, right? That's what we call the catenary robot, because the curve that the rope describes is called a catenary. And then they can start to interlace with each other, right? But in this setting, the distance or the obstacles are not as important as knowing if the cable is above, one of the cables is above or below the other, right? That's going to determine that if I pull, I'm going to have a cable in my hand or I'm going to have an object, right? So for that, we need to understand the topology of the system, and that's where we plan based on topology, right? Not based on a metric system, because a centimeter will not be much in a metric system, but for the cables, it will be completely different, right? So that is one of the main challenges.
Can you talk to me a little bit about how the drones interact with each other and become to where they're working in a single unit?
The main idea here is that we have a team of AIM catenary robots, and their objective is to interlace their cables to be able to transport an object, right? For that, they need to calculate a plan about how to move one cable about the other. It's like knitting. Like we need a sequence of cable goes up, cable goes down, and they should be able to figure out autonomously, right? That's done based on the team, like the teammates that they have, and also based on the object, because the object has a specific shape that they need to go around and start to wrap to create a knot that will help to move the object.
Thinking about them interacting with each other as a team there, would one unit maybe have a specialty? Like thinking about knitting, like there's a certain dexterity that's involved with that. Would certain robots need to do certain parts of it, or would you ideally have everybody could do whatever?
So far, we define two types of drones. So two drones are like strong. They are the ones who are going to pull and carry the object. And some other drones are just helpers, right? We can think when we tie our shoes, we pull the two ends with the string, right? But while we make the knot, we don't need that string. We just need to hold it in one position while the lace passes around. We have the same thing. Some drones will only be able to hold the cable while the others go around.
initially you mentioned how heavy like an arm or a grabber is. In the cases of these helpers that are doing some of the finer detail, what kind of attachment or tool do they need to do that job?
We want something that's part of what we are trying to do, something that is very lightweight, maybe like a 3D printed, like little piece, like a hook. That the objects only to hold the cable for a little bit of time. So maybe they just pass the hook, hold it, and then they can just release it.
For the control of them, do you have to operate them independently, or is it more of you program it to do something and it moves along?
Our objective is that you tell me I need to move this chair from this room to this other room, or I need to move this tool to the top of an skyscraper, right? And the robot should be able to figure out where to pass the cables to wrap the object, to make a knot, and be able to move it, right? So for that, they need to coordinate. They need to understand what the others are doing. We have different approaches for that. One of them is we define our own type of hitch. That was the special part that we have been doing the last 3 years. Because what my PhD student did was like he went to all the marine knots and checking which one we can do with drones, right? And after some research, he figured out that none of them was like easy to make and easy to untie. So we started to think like how we want to control the friction. At some point when we pull, we wanted to release the object, right? But so depending on the actions that we do, we still want to hold it or release it. And then we design our own hitch. And that hitch is based on a polygon that we can adapt to any object. And the robots know the polygon, and they will know that they belong to one side of the polygon. So they can do it in parallel. They can do their job without thinking about the others. It's like, I need to place my cable here, then I need to wait for my neighbor, and then we can make a twist, right? And to start to interlace the cables.
Have you had any cases where one of them runs into an issue where maybe it's damaged, maybe it shuts down, maybe the battery dies or something, but something happens to where it can't do its part? What does the first one do at that point?
I think right now there are more failures than success. Yes, like all the things happen. Like one of a funny one is that you have 8 robots trying to lift an object, right? And one of the drones stop working. And then now you have 7 drones trying to lift the object and a dead robot, right? And they still can do it. So it's quite interesting how the system can adapt. So they stop working. The cables slide when they shouldn't, or the cables they get stuck when they should slide. And that's where our research comes, like how we can make the cables do what we want, right? When we want to slide, we will do it. We humans, we have some actions like we shake objects, we pull harder, but robots still don't have those abilities yet. We are using reinforcement learning for that. So at that moment, it's like we have the model of the vehicle, we have the model of the cable, but there are so many variables inside, like the friction, how the cables are interlaced, that what we tell the algorithm is like, now you have to learn, now you have to do some interaction and see what is the best action that will move that crossing point where we want.
So what are the challenges with that training? Are you using reinforcement learning primarily?
On one side, what we use to interlace and determine how the robot should move around, we use topological planning. And for the part where we need to slide the cables, we need to tie, we need to apply different actions with them, that's when we use reinforcement learning. Specifically, we use model-based reinforcement learning, and we try to combine the model and all the dynamics and the mathematics that we know with what we don't know. Right? That's the challenge.
Right, getting that real-time reaction.
Yes, especially aerial robots come with challenges different from the reinforcement learning applied to Atari, where you can run in millions of times and eventually it will solve the video game. In aerial robots, the batteries don't last that long, so they need to learn fast. They cannot make big mistakes because then they will crash. So these are the main challenges here, like how to do it fast, how to do it accurately and safe.
Right, the stakes can be a little more catastrophic.
Yes, especially when we are trying to move objects in the air and everything falls and break.
What would you say is the biggest benefit maybe of having a collaborative robot system?
There are multiple advantages. One of them is the versatility. We can associate number with how big or how heavy is the payload, right? In some cases, maybe 2 robots are enough to move an object. Maybe I want to move a piano, then maybe I need 100 robots to do that, right? Or we want to pass the cables into different parts to make it safe. So that versatility that I can add and remove drones on demand is the main advantage of the Swarm, right? And the cooperative work. Once they define the objective, they can do it as a team.
Can you talk about some of the challenges interacting when it's multiple units in a team?
One of the main challenges is the logistic. More robots mean more components, more batteries to change, and especially more points of failure, right? So we are trying to be resilient to that. And as I mentioned with the example, like if one robot fails, the system should still work, or a few robots fails, the system should still be able to make it the task that we asked them to do.
One of the kind of ideas that people on my end of things got excited about was how this might be used in disaster response or emergency response. Can you talk a little bit about where you might like to get the technology to in that regard?
Especially in disaster response, right? Having multiple robots, we have this versatile part, right? We don't need to come like, oh, we are going to move this type of objects. No, it's like whatever that we will have in front of us, we will adapt to them, right? So we have a versatile solution, and we will be able to move objects and manipulate things that autonomous systems were not able to do before. For example, we can move those plastic covers to protect houses in when there is like heavy rain and stuff. Robots are be able to move that. They bend. They are not easy to manipulate. The wind comes from one side, and now the robots need to adapt to that. So these type of objects are very challenging to move, but when there is a disaster, we will be able to move those objects that in the past we were not able to.
You recently got a career award. Can you talk a little bit about what getting recognition from NSF means to you?
It means a lot. Like we have been working in this type of problems. Some of the problems are a little bit of science fiction. Like some people don't believe, oh, you can do that. Cables are too complex, but then we keep working and then we get some advances, and some people start to think that it is possible, right? So having the support from NSF to push these ideas forward, it has been great for me and for my lab, right? We in my career award, we work in a similar problem. It's not exactly the same problem with the cables. In that case, we deal with objects that are soft. When we try to move objects that they don't stay rigid like a box. Sometimes like a a piece of wood that can bend. People try to move their mattress when they move from one house to another. It always bends. And we need to give the robots the capability to move objects that are non-rigid. And we got the support to move these ideas forward.
Thinking about the future, what are kind of your next steps as you develop these robots?
This is a very recent research area. In the last 3 to 5 years, what we want is to have this work working in the lab, right? We want to start moving objects in the lab. We want to be consistent. As I told you, now we have more failures than success. There are so many variables that we need to understand how to make reliable controllers and safe controllers. Right? So we are working on that, developing the theory to support these autonomous vehicles. And then our plan for 10 years is to have this in the real world, right? They not being in the sci movies anymore. We want them to be part of the real life, right? We want to move an object to a house, and it's like, oh, I just call my team of drones, they do it, and they go back to their station.
Special thanks to David Saldana. For the Discovery Files, I'm Nate Potker. Please subscribe wherever you get podcasts, and if you like our program, share with a friend and consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.